but you know, don't feel obligated. Or are you really registered?
What?
Are you registered?
Yeah.
Oh, you are. Oh, okay. All right. I thought maybe you were just sitting in. Are you in the lab? Which lab? Oh, okay, good. You want to join our my meetings about the FPGA design we're doing?
Sure.
Yeah, because we're right at the point where we're looking at the, you know, Brent's rule and interconnection architectures and trying to figure out the right thing to do there. And
I remember when we were talking about that bit like last semester or a year ago.
yeah, I really want to get my head around it and see if there's something we can do there that's better than. It's the same question, you know, why that you asked when you walked in the office. Why don't we just build hierarchical things? Oh, I'm late already. Okay, we're going to start. So last time we started talking about CMOS, and I think what we covered last time was talked a little bit about processing ICs. I gave you a very simplistic view of how chips are fabricated. And this is mainly for background. If you're really interested in this, there's some nice courses here you can take to learn this in greater detail. And then we started talking about CMOS transistors, and we talked about the various models that we use for transistors as switches or as resistors. And then eventually, as I go through this, we got to some simple circuits. And the type of circuits we're talking about were, were so-called static CMOS, where, sorry, I have to go through this. Okay, so the circuits look like this, and this is a description of a single CMOS logic gate, and the simple ones you probably have seen already, like NANDs and NORs and inverters, but we said we can actually implement any logic function in a configuration that looks like this, where there's a pull-up network and a pull-down network. Those two are never on at the same time, but one or the other is on always. Meaning, when I say on, I mean it's conducting. So there's always a path from the output to either ground or a path from the output to VDD. And which one of those it is depends on what the inputs are, right? So for every input combination, there's either a connection to VDD or a connection to ground at the output, okay? And then we can implement any logic function we want by how we arrange these pull-up and pull-down networks. So we talked about that last time. You looked at NAND and NOR. And this was one example that we had here. And we said that in order for these two networks to have this property of being complements, right? They're the dual of one another. If you think of this as a graph, this is a dual of the pull-up is a dual of the pull-down, right? So the simplest way to think about designing these gates, if you look at the logic function we're trying to implement here, the ands and ors give us an indication about transistors being in series or being in parallel, right? So here it says D OR. We know if it's an OR, it's either this path to create a 0, and this function is trying to create a 0. That's what the bar over the function says, right? So whenever this is true, we complement that, and that makes a 0. So we're looking for ways to make a 0. So we can make a 0 either by D being true, or by A being true, and then B or C being true, right? Or being conducting in this case, since it's a switch. So that's the way we think about building these logic gates. And then the pull-up is just the dual of that. And you can get the dual of that very simply by just replacing the ORs with the ANDs, right? So here D is in parallel with everything else. Here D is in series with everything else. Here A is in series with B and C. Here A is in parallel with B and C. And B and C here are in parallel, and here are in series. Right? So that forms the dual network. And that property guarantees what I said at the beginning, that either this is conducting or this is conducting, but never both at the same time. Now, I said there's another way to form a dual, which I showed you quickly. And I'm going to do one more example of that because I want you to see another example because it's kind of cool, but I don't have a pen. Let's see if there's anything in here. I can't get in there. Let's see if I brought a mark. I need a marker for the board. That's what I'm looking for. Oh, damn it. Ah, great. Thank you. So let's just try. I'm going to try this one here. Look at this network. So the way you do this is we're going to make a simple graph where the edges of the graph will represent the transistors, and we'll use dots to represent the nodes. Remember, electrical node is a place where components come together. So there's an electrical node for the output here. And there's an electrical node for the ground connection here. And then we have an intermediate node there. So we're going to put another one here. And then we'll put the arcs, arches, I guess you call them arcs, which represent the transistors. And we'll label them. So that's D, and that's A. And you can see A is in series with B and C. Okay. Now, the way this method works is that these two nodes, out and ground, they divide the plane in half. So we're going to divide the plane in half. Now, if we look at this, we have some regions. We have a region here. We have a region here. It's enclosed by those arcs. A region here, and then a region over here. So what we do is we put a node in each one of those regions, a new node. We're going to turn sideways 90 degrees now. So we're going to put a node over here and let this can be either VDD or out. So we're going to have the top node. So we're looking at trying to form this network here. We're going to have two nodes there. So let's just call this one out, and this one VDD. And then we'll put a node in every other region, like that. Those will be intermediate nodes. And then we're going to connect all the dots. Now, when we cross these edges, we have to label this new edge with the same as we had before. Oh, why is this not working?
You only do the adjacent ones.
Only go to the adjacent. Oh, thank you. Yeah. This is planar graphs. Okay, so yeah, you connect the, thank you. Connect the dots between adjacent regions. So that, I don't need that edge there. Okay, so here's an edge D. This edge is going to be B, this edge is going to be A, and this edge is going to be C. And then we can draw the circuit that's associated with that new graph that I drew at 90 degrees. So I have VDD, and it has a D transistor, and it has, in parallel with that, B in series with C. And then in parallel with that, an A transistor. And then this is out. And I think that matches, it matches this, except it's upside down, and it really doesn't matter. It's the same. It functions the same. All right, so that's kind of a graphical way to form a dual using dual graphs. And sometimes it's easier to do that if you don't have a convenient way to get the Boolean expression or it's too complicated. So I just thought you should see that method. Okay, so that was this slide. I have another example here if you want to see that. Okay. So the other thing I talked about last time, which is important to understand, is that we can't really build non-inverting logic. And what that essentially means is the pull-up network, we can't use N-type transistors, and the pull-down network, we can't use P-type transistors. And that came from the fact that there's a threshold voltage associated with these transistors. If we try, as shown here, to use an N-type transistor to pull up this, in this case, there's a capacitor here, and we're charging up the capacitor. That's pulling up the voltage. We'll get to a point where the voltage on the capacitor, once it gets to VDD minus VT, within one threshold drop, or one threshold of the transistor turning on, it essentially turns itself off. So this voltage will effectively not rise above VDD minus VT. So the logic level is degraded. Likewise, using a P-type transistor to pull down, it doesn't actually pull all the way down to ground. It stops at whatever the threshold voltage for that transistor is. In the case of the technology we're using, that's probably about 1/4 volt. Okay. And to make things worse, if you built a gate this way and then cascaded it with another gate, you would get a second voltage drop at that gate. And then if you went again, you get another voltage drop. And pretty soon, your voltage swing on your signals would be very small. So that's why we don't do that. So the rule is we use N-type transistors in the pull-down network, and we use P-type transistors in the pull-up network. All right. So that was all last time. And that means if you do need an AND function instead of an AND, okay, the way we implement that is to build an AND, which is 4 transistors, and then 2 more transistors to invert that to turn it into an AND. Right? But typically, we'll try to find a way to absorb this inversion somewhere else by moving bubbles around in the circuit. Okay, so today, here's a new idea. So that was all we call static CMOS. And all the logic gates take this form, as I described. There's another way to use transistors to build CMOS circuits, and it's based around the idea of a transmission gate. Okay. And a transmission gate, now I just told you that we can't build ideal switches with just one type of transistor or another. Right? The N-type transistor is good for passing zeros or generating zeros. The P-type transistor is good for generating ones. If we need to pass both values through, then we need to use both transistors. Okay? So this configuration here is what we use in some circumstances, which I'll show you. And we call it a transmission gate. And it works this way. It has a signal here. There's a complement of it here and the signal here. So if enable equals 1, right, then A connects to B. Okay, so this is a way to build a perfect switch. See, because if we just had an N-type transistor there, it still works like a switch. But if we were trying to pass a 1 through here, we put a 1 here, which would be VDD. We get VDD minus VT at this side. So it wouldn't be a perfect switch in terms of passing the correct voltage. So if we put both transistors there, we can handle both cases, either passing a 0 through or passing a 1 through. And when I say pass a 1 through, what I mean is connect this side to VDD and expect this side to be VDD. Or connect this side to ground and expect this side to be grounded. Right? That's what I mean by passing a 0 or a 1. Okay. So this is a popular structure in CMOS for building perfect switches, and I'll show you what we can use, how we can use this to simplify some of our circuits. So the first example is a transmission gate multiplexer. Right. So we've talked about multiplexers a lot. They come up quite often. This is a 2-to-1 multiplexer, and it has this logic expression. This logic expression describes its function. It says, here's a symbol of it. It says C is equal to S A plus S bar B. What this means is if S is equal to 0, then B gets connected or gets sent to C. If S is equal to 1, then A gets sent to B. Okay. Based on this, we could build a circuit that implements that, and I'll draw it. I think you've seen it before, but using simple logic gates, it would look like an and or. That's a sum of products there. That's the or, and here's S, and I like to draw it this way. That's A, and that's B, and that's S. Okay, and we know in CMOS we would probably not use and or because that would be 6 transistors, and that'd be 6, and that would be 6. So chances are we'd just turn this into an and, make it a little more efficient. Because we know NAND is equivalent to and or. So we'd have an extra inverter here, plus 4 transistors, 4 transistors, 4 transistors, and that would give us a multiplexer. Okay, so far everything I've told you this semester, this is as good as we could do. Okay, but now we're going to show how you can build a circuit that has the same function that is simpler, meaning fewer transistors would take less area on the chip, less power, probably be faster. All right, so if you think of a multiplexer not as this, and not as this expression here, but more like this. It's some switches where what we do based on S, either we connect A to C or we connect B to C. Then we can use our transmission gate, perfect switches, and build a circuit that takes on this form. So here's one transmission gate, here's another transmission gate. These exactly implement these 2 switches that I show here in that schematic. Okay. And then S is used, as you can see here, we take S and form its complement. So we have S bar here and connects down here, and then S connects here and here. So these 2 switches are never on at the same time. If S is a 0, then you get a 0 here, that's on. You get if S is 0, we get a 1 here. So that's on, and both of those are off or closed. Right? Otherwise, if S is a 1, then this one switches on. Right? So then it just connects the input to the output. So that's kind of nice. It's a lot simpler. If you count the number of transistors here, like I said, we're going to have 2 plus 12, or 14. In this version, we have 1, 2, 3, 4, 5, 6. Right? So it's a lot smaller and probably faster as well. Right? So that's one of this kind of technique gets used in CMOS circuits, and there's other examples of this. Now, this type of idea is pretty powerful, but you have to be careful. If you strung a lot of this type of circuits in series, okay, you can end up with a long logic path. Right? So if A were 0 and this thing were on so that this is the conducting path, essentially what has to happen is A has to well, how should I say it? I'll just say it briefly now, and we'll see more next week. If we cascade a bunch of these circuits together, we can get a long delay because we get a long string of these transmission gates. And the delay on that type of structure is going to grow with the square of the number of transmission gates in series. So occasionally then what we would do is break the chain and put a rebuffering and put an inverter or some other circuit in there that connects to VDD and ground. Okay, so here's that was a 2-to-1 multiplexer. We can extend this idea to make a 4-to-1 multiplexer as shown here. So what we do is use 2 transmission gates in series for each input. Right? So if the S is 0, 0, then these 2 transmission gates are on. Right? If it's now, if it's 0, 0, those 2 are on, but this one is also on, but that one's off. Right? If it's 1, 1, those 2 are on, but that one of these is also on. I don't remember which one. I'm going to figure it out right now. Right? So it's kind of, it's the series connection of the pass transistors forms the AND of the S1 and the S2, right? Or the S0 and S1. Now this one, I need to plug in here. Again, if you could do the analysis, I'm not going to do it, but you could look at the number of transistors here versus the number of transistors if you built the 4-to-1 multiplexer in the way that we've discussed it in the past, right? Which probably would be using 3 of these circuits, right? So, well, we could do it 3 times. This would be 42 versus whatever this is, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So it's like half the number of transistors. And it's probably faster, too. Now, it turns out there's some variations on this. There's an alternative solution, which is kind of interesting. It's also a 4-to-1 multiplexer. You could do it this way. This one has, if you look at the path from input to output, here each input to make it to the output only goes through a single transmission gate, right? Versus this previous one that went through 2, right? So you might think that this is faster, and it is faster. There's less delay from these data inputs to the output, but there's more delay associated with this part. So this is essentially a decoder here. We take the 2 S bits, right, which is a binary code, 0, 0, 0, 1, 1, 0, or 1, 1, and we turn it into a 1-hot code. One of these will be turned on. The appropriate one will be turned on. Right? And you need those extra NAND gates and inverters in there in order, well, AND gates and inverters. You'd probably do those with NAND gates, but there's an extra level of logic in here in order to decode the S signals. But if you do that, then the dividend is there's less delay here. So this is the type of circuit you would do if these signals came early, those were available early, and you wanted to minimize the delay on the data lines. You could use this kind of one versus the other one. Right? Okay, so just a small variation, something interesting to think about. Right? All right, so that's transmission gates and multiplexer type circuits. There's another place where we essentially use transmission gates, and it's in so-called tri-state buffers. And these are interesting circuits that they kind of violate our principle of static CMOS in an interesting way. So the symbol for that, for this one, it's a non-inverting version. It looks like an inverter without a bubble on it, which sounds kind of silly. It has no logical function, but it has this electrical function. Has an extra input here called output enable. And here's the truth table. If output enable is 0, then, well, if output enable is 1, then the output just follows the input. But if output enable is 0, what we do is put the output in what we call high impedance mode. Essentially what this means is the output is disconnected. Nothing is driving that node. Right? Remember when we were talking about static CMOS, I said it's important that every node is driven at every time. This is where we violate that. This is a circuit that will allow us to intentionally disconnect that output node. And I'll show you why we may want to do that in a minute, but let me just show you there's variations on this. In fact, in CMOS, most of the ones are inverting. So this is you can think of this as a special kind of inverter, and it has an extra input. And when that input is a 0, then the output is so-called Z, or high impedance, or it's disconnected. The way we build that is essentially looks like an inverter with a transmission gate here, where this transmission gate gives us a way to basically disconnect the output. Right? So if the enable here is 0, then this transmission gate is open circuit, and the out signal here just floats. There's nothing driving it here. So in practice, that'll be driven by some other circuit. But this circuit will not be driving that. That value of out is not determined by in. It'll be determined by something somewhere else. Right. And the way we provide this isolation, it's usually done this way. This is kind of structurally, functionally, this is what we want. But usually, we make the circuit this way. If you look at this, this is an inverter. There's the P and the N. Right? And then these two transmissions from the transistors from the transmission gate, we just pull into the inverter and put the P here and the N here in series. Right? These two are very similar. It just, this one usually works out better. It lays out better. Right? So here again, if enable EN is true, or a 1, those two transistors are conducting, and this just looks like an inverter. It'll just pass a value through. If enable is 0, these two are open circuits, and it doesn't matter what we do at the input, the output won't be affected at all. Okay, so these are used, but they have to be used carefully because we have to make sure it's a bad idea to ever leave a node floating, so this signal has to be generated from something else. Usually it's generated from another tri-state buffer. So here's an example of that and why we like these. They enable bidirectional connections. Right? And what I mean by that is we may have a data signal that we want to send from here down to here sometimes, and at other times we want to send the data signal from here up to here. So it lets us use this wire here to go either way. And I'll show you how that works. At each place we're going to have a tri-state buffer and an inverter. The tri-state buffer will act like the transmitter, and the inverter will act like a receiver. So when we want to go from top to bottom, we'll turn on that, and then the signal will come here. When we want to go from bottom to top, we turn off the top one, turn on the bottom one, and then the signal will go up this way. And I think you can see that here. Okay, so if we want to go down the red line, set the down signal to 1, set up signal to 0. So that disables this. So it just disconnects in 1 from its output. So this node is floating, but it's not really floating because it's being driven by that tri-state buffer there. If we want to go the other way, we just switch the sense of up and down here. We set the down signal to 0. That turns off the top tri-state buffer. Set the up signal to 1. That turns on the bottom tri-state buffer. And then any change here will get propagated to this point here. So that's one of the big uses for tri-state buffers, is to enable kind of bidirectional signaling. Often they're used in this way when multiple circuits all connect to a common node or a wire. Right? So you see this kind of configuration where you have lots of, these are connections to subcircuits, and all these subcircuits are connecting to one another at various points in time over the single wire here. So everybody can listen to the value on the wire, but only one of them can drive the signal on the wire. If you turn on two tri-state buffers at the same time, they're going to fight. In fact, you probably get a short circuit. If this one's trying to drive a 0 and this one's trying to drive a 1 and they're both driving at the same time, what will happen is by driving a 1, that means it's connecting its output to VDD. And this one trying to drive a 0, it means it's trying to connect its output to ground. So the current will go from VDD through that wire down to ground. And the chip will heat up and eventually it might burn out. But the logic value you get here will be something weird. It'll be some indeterminate intermediate voltage, and that's a bad thing to do. So the rule is only one of them can be on at once. Yeah. So one driver, lots of listeners. Right. So it's a kind of a way electrically to broadcast a signal. You can send that signal many places. And you can send it from different places. Right. Now, tri-states make very nice multiplexers also. In a similar way to how we made multiplexers out of transmission gates, we can make multiplexers out of these tri-state buffers. Okay. Here again is kind of a schematic view of what the multiplexer does. And this is a way to implement it using two tri-state buffers. We have one that has an inverting version of the control signal and one that has a non-inverting version of the control signal. Right? So if S is true, then A drives its output out. If S is false or 0, then B drives its output out. And this is a little more, it's more transistors than the transmission gate mux that I showed, multiplexer I showed you. But it has a nice property that the output is always, it's a restoring circuit, meaning the output always comes directly from VDD or ground, not from some other circuit that's coming in on its input. Right? So it's a little easier to use, a little more robust. So this is more popular, actually. If you look in the standard cell libraries for the ASICs that we build, the multiplexers are often implemented this way. Now, this circuit here is just an implementation of that. It's a little tricky to see. The left-hand side is the top tri-state buffer. The right-hand side is the bottom tri-state buffer. The S signal, we assume that we have S and S bar, so there'd probably be another inverter associated with this, which would invert the S signal. And then that gets crossed here, because it's used, each S and S bar are used in, each one's used in two different places in here. Right? So we just cross it and use it that way. Okay, so also a very nice, very popular circuit because it's compact and very robust. Okay, so that brings me to latches and flip-flops. We haven't talked about the circuits of flip-flops. It's important to understand how we build flip-flops with transistors. Okay. And we're going to start by talking about how we build latches. First, I think I've defined this earlier, but I'm going to define what a latch versus a flip-flop. They're not exactly the same thing. They both store values. But a flip-flop has this characteristic of the edge-triggered behavior. Right? We know a flip-flop captures its input value on the edge of the clock. A latch can capture its value according to the level of the clock. Right? So that's illustrated here. And the symbol that I use for it is just same as the symbol for a flip-flop, except there's no little triangle on the clock input there. And that's how you know it's not a flip-flop. It's just a latch. Okay, this is the characteristic of a latch. If it's a positive level, we call it a positive level sensitive latch. The level sensitive means it's sensitive to the level of the clock, not to the edge of the clock. And this one is sensitive to the positive level of the clock. So when the clock is high, if we change the data input, the internal value will change and the output will change according to D with a little bit of delay. And then when the clock is low, the latch ignores the input. It doesn't change its value. Right? So here, when the clock goes low, it just holds whatever value it had before the one, at the end of the clock being high. Right. So that's a latch. And we can build that in CMOS this way. There's other ways. I'll show you another way to do it later, but this is probably, in principle, the most popular way that it's done. Okay. There's two inverters. And we've talked about this before. If you take two inverters and you put them in a ring, in a cycle like this, they form this kind of infinite reinforcement. Right? If you put a 1 here, it makes a 0 here, and the 0 here makes a 1 here, which makes a 0 here. So it's a very stable circuit. And if you try to upset it, a little bit of noise on this one, it'll go through here, and that'll, because of the restoring property of the inverter, that'll turn that into a very good 0. So this is very immune to noise. As long as you leave the power on, it will remember its value. Okay, so we like this as a way to build a latch. And that's what we have there. The only question is, how do we change its value? We put those transmission gates in there to allow us a way to make it level sensitive, to make it sensitive to the clock. Right. So what this says is, when the clock is high, we allow a new value to come into here, and we turn off the feedback. By turning off the feedback, it's essentially breaking this line there. And so then it becomes, well, actually probably more like this, breaking that one there. It makes it very easy to put a new value in because you're not fighting. Otherwise, if we didn't do that and you try to change the value somehow in here, you'd have a fight between this and whatever circuit's trying to change the value. So by cutting the feedback, we break the fight. Right, so when the clock is high, this transmission gate is conducting, and this transmission gate is not, so there's no feedback. And then when the clock goes low, we turn off this transmission gate so that any changes here won't try to change the internal state. And then this just forms the feedback, so it just remembers its current state. Right. So that's pretty compact, and that's with 8 transistors. Okay, so how do we use this to make a flip-flop? Well, we use 2 latches in series to make flip-flops, edge-triggered flip-flops. It kind of looks like this. There's a sampling circuit and a holding circuit. Or some people call this a master and slave. And the way this works is when the clock is low, we have this configuration. Clock is low, clock bar is high, therefore, and then remember these 2 latches, oh, I didn't say that, but the first latch, this latch here is a negative level sensitive latch, and this is a positive level sensitive latch. You can see that because the clock connections are inverted here. That's clock bar here, that's clock bar here, that's clock, etc. So when the clock is low, this transmission gate is on, this one's off, so we have this configuration. Any value of D just kind of passes through here. Right? But while the clock is low, this transmission gate is on and this one is off, so the new value the new value just stops there. Okay, and the old value is just held. Right. That's why the clock is low. Then at the instant when the clock goes high, so what we're doing here is we're getting ready to capture a new value because we know the rising edge of the clock is coming. So the new value is getting set up. The new D value is coming in, and it's kind of making it to this point. But we're still showing the old Q value at the output. When the clock goes high, we kind of switch the operation. So what will happen now is on the rising edge of the clock, we turn off that transmission gate, close this loop, we've captured the new value in here. Turn on that switch turns on, this turns off, and then it just shoots all the way through to the output. So you can see right on the rising edge of the clock, that's when everything interesting happens. Right? And then at some point in time, the clock will go low again. What happens when the clock goes low? Well, then we go back to this state we had here, and then the new value, which was previously being held here, now just gets held in here when the clock goes low, right? And that's how, so it's held all the way again until the whole thing starts again on the new positive edge of the clock. Right. So that's kind of a tricky, really clever circuit that we can use to provide this level sensitive type behavior that we want. I'm sorry, the edge trigger behavior that we want by using a master and a slave or two latches back to back. Okay? Make sure you understand this. I mean, it's not simple and I went through it fast, but just take some time and look at it in the notes. I'm sure you can get it. And we'll revisit this later when we talk about timing and how long it takes to get signals in and out of this circuit. Now, the only thing I wanted to show you on flip-flops also is there's an alternative way to build the latch, and we can build it, and this is actually more popular these days. We can build a level sensitive, and this is a positive level sensitive latch this way. So instead of using transmission gates, we use tri-state buffers. So similarly, how we built a multiplexer using transmission gates, and then I showed you how to build a multiplexer using tri-state buffers. It's a similar thing here. We can build latches with either transmission gates and inverters, or we can build it using tri-state buffers. And this is a tri-state buffer version. So there's a tri-state buffer here and one here in the feedback. So when the clock is high for this one, this is off, and oh, this is actually negative level sensitive, isn't it? Sorry, I'm gonna fix that. Okay, so when the clock is low here, this tri-state conducts. D goes to here and through the inverter. This one is off, so there's no feedback. And when D goes high, or clock is high, in this case, sorry, there's feedback, and this one is disconnected. Right. So it's the same function I had before. This is commonly used in standard cell flip-flops for ASIC design. Two of these, this is the negative edge, then there'll be a positive edge, or positive level sensitive latch following this one. And then the two together will make up the flip-flop. And there's probably also an inverter there to make an inverted version of the clock. It's more transistors than the past transistor version, but it's more robust to noise, and it's a little safer. Okay, and it also lays out well in modern design rules, layout rules. Okay, so I'm going to change the subject. Any questions on any of this today? So this is all, the new stuff was the transmission gates and tri-state buffers. Okay. So what I'm going to talk about. So that was sort of the introduction to CMOS. So now what we're going to talk about is timing. So before I do that, I just wanted to make a comment here, since we were talking a little bit about physics last time and transistor devices. And the course isn't really about devices, and it's not about processing, and it's not about physics. And it's because as a ASIC or FPGA designer, you don't really need to know a lot of physics, but it's good to know what's under the abstraction. We have simple models for how transistors work and how circuits work, but it's good to understand where the limitations come from, because the physics really affect the area, how big something is, and that affects the cost, and the delay and that of the circuits, and that's going to affect the performance, and the energy consumed, and that's going to affect the performance and even the cost. And these are as we talked about the first week, area, delay, or cost, performance, and power or energy are really the big factors that we're trying to optimize for, right? So it's good to know a little bit about what affects those things, right? Ideally, our circuits would have 0 delay and 0 area and 0 energy. Of course, physical devices occupy area. They take time to do what they're going to do, and they consume energy. So we can't get to that point where we have infinitely fast, zero cost circuits consuming no energy, but it's important to see how close to that we can get. So in CMOS, the CMOS processes, as I described, it lets us build transistors and wires and connections. In the process of when we build that, we also get capacitors and inductors and resistors, even though we don't necessarily want them. Right? Sometimes we do want capacitors, which we'll talk about later when we talk about memory. But usually when we're considering logic circuits, we don't want capacitors, and we don't want inductors, and we don't want resistors, but you get them anyways. So we need to understand the effect of the capacitance and the resistance on our circuits. Right? And that's how we go about understanding the timing and the power consumption of our circuits. So back to this diagram I showed you before. This is kind of my generic model for a digital synchronous system. As I said before, and hopefully you believe by now, anything we want to build in a digital circuit, we can think of or model as a set of combinational logic blocks and a set of state elements or registers in this case. And on every clock cycle, we're effectively changing the state of these registers. Right. So in between the edges of the clock, we move the values from a register through the combinational logic, and it then appears at the input of a register, and when the clock edge comes, we change the state of that register, and all of those are happening in parallel. Right. So this thing is like a big finite state machine, if you wanted to think of it that way, right? Where we change the state of the system on each clock edge. Now, there's some performance associated with this. We said at the beginning, in the first week, that one of the things we optimize for is performance. So how do we measure performance? What do we mean by that when we say performance? Well, that's a really complicated question. It depends. You could say operations per second. If this is a widget that does maybe it does multiplication, right? You could say how many multiplications per second, that would give you the performance, right? Some people, we say, cycles per second. It would just, the circuit's running at 100 megahertz, therefore that's its performance. So we make it go at a gigahertz, then we've increased its performance by 10x. Sort of. It's not so simple. It is directly proportional performance, that is directly proportional to the clock frequency. It may not be the entire story. If you've studied computer architecture, you know this to be true because we talk about CPU performance, at least as defined by Dave Patterson and John Hennessy, is the number of instructions times the number of cycles per instruction times the clock period. Right? They talk about performance to run a particular program or a set of programs. Right? Clock period or clock frequency is really only one component of that. There's other characteristics, because for a given program, you may have a very high clock speed, but if it takes lots of instructions to execute that program, or many cycles per instruction, then that high clock speed won't necessarily give you higher performance. So my point here is it's a little more complicated. How do you define performance? Usually in this class, when we talk about performance, we're going to talk about clock period, or clock frequency, 1 over clock period. Okay, to that end then, oh. All right. We'll think about limitations on clock rate. We'd like our circuits probably to run as fast as they can for a given amount of power and a given amount of area to find that kind of Pareto optimal point. Okay, so what limits the clock rate? Well, there's two things. There's the logic gate delay, and this comes from the fact that if we have a logic gate and we change its inputs, the outputs will change, but they'll change after some period in time. We can't instantaneously change the output. And we'll look in great detail why that is. But graphically, it kind of looks this way. Change the input waveform, the output will change after some delay. And it's kind of instructive to think about what typical delay values would be for modern day process. If you look at like a 7 nanometer process like we've been talking about, does anybody want to guess what the gate delay would be, what the delay through one gate would be? You could figure it out. I mean, if you really had to, look, that's the processor we build for making microprocessors. You know how fast your processor runs in your phone probably, right? What the clock frequency would be, does anybody know? Just give me a number.
A gigahertz?
Gigahertz, yeah, probably 2 to 3 these days, but yeah, gigahertz range. Okay, so we'll take gigahertz for a minute. Okay, so gigahertz, that's 1 over a nanosecond, right? Because the clock period of a gigahertz clock is 1 nanosecond. And you would think, what has to happen within 1 clock period in a microprocessor? Well, you're going to go through a few logic gates at least. Every operation, you can do an addition in 1 clock period. We've looked at ripple adders. Even if we built a fancy adder, you're going to have to go through some number of logic gates, usually like the log of the number of inputs into your adder, but roughly. So probably 6 or 10 logic gates in series in 1 clock period. So you can guess that logic delay has to be somewhere in the, a tenth of a nanosecond or, tens of picoseconds or somewhere in that range, right? Okay. So I'll tell you what it is in a minute. But, okay, the other place we get delay is in flip-flops, right? Remember my circuit here. What's going to happen on each clock period is we're going to change at the rising edge of the clock. We're going to change the values in that register. The outputs will change. There'll be a little delay before the outputs change, some delay to go through the combinational logic block, and then it has to get to the register early enough to get inside the register. I showed you how signals go inside the register into the flip-flops. Okay, so the other thing that contributes to logic delay is the delay associated with the flip-flops. And there's 2 times that are important. It's the so-called setup time and the clock to Q delay. The setup time is the time that the signal has to be early before the rising edge of the clock. That's to allow the signal to get inside the flip-flop. It's a characteristic of a given flip-flop and a characteristic of a given process. Like 7 nanometer process from TSMC, their flip-flops built a certain way have a certain setup time, and that's characterized. And as a designer, the tools will know what it is, and you'll know what it is if you need to know. Okay, so this is a short amount of time. Signal has to get early before the rising edge of the clock so that the flip-flop can capture it properly. And then once the output gets changed on the rising edge of the clock, there's a delay before the output actually makes it out of the flip-flop. And that's the clock to Q delay, because it's from the clock to the Q value changing. Okay, those two, along with the logic gate delays, or the accumulation of logic gate delays through series of logic gates, is what will limit the maximum clock frequency. Okay, so what must happen in 1 clock cycle for correct operation? All signals connected to flip-flops or memory inputs must be ready and set up before the rising edge of the clock. Okay, for now, we're just going to assume that there's a perfect clock distribution, that all the flip-flops see the clock at the same time. In fact, later we'll see that because the clock distribution is not perfect, flip-flops get slightly delayed versions of the clock, and that actually also contributes to what the maximum clock frequency can be. Okay, so here's an example. This was the parallel to serial converter circuit that I showed you previously. Here's just a piece of it. I'm not showing you the whole thing. But this was repeated over 4 bits, I think. And remember what we had was a series of flip-flops that were cascading with one another that kind of form this shift register. But we can load values into the shift register with these multiplexers here. So if the load signal is asserted on the rising edge of the clock, the registers get their values from these inputs, the top input of the multiplexer, and go into the flip-flops. If the load signal is low and the signal gets clocked, then this value just moves over to here. The value from here moves into here. They just all move one station to the right. Okay. Now, there's some timing associated with this, which we can view this way. Here's the and what I'm looking for at here is the time associated with the loading of, well, either loading a new value in or by moving values to the right. You can see, if you look at, here's the clock, here's the signal A. When the rising edge of the clock happens, the A value will change sometime after the rising edge of the clock, and that's the clock to Q time, right there. Then there's some delay through the multiplexer, right? And so here's the B signal on the other side of the multiplexer, and that's changing here. This time, between the change at the input of the multiplexer to the change at the output of the multiplexer, that's the mux delay, right? And then we've got this constraint here that the value into the new value into the flip-flop has to be, that change has to happen before the setup time here. And you can see in this case there's plenty of margin, right? In fact, there's extra slack in this circuit. We're clocking it slower than we could. If we wanted to, we could actually, in this case, make the clock period smaller, and we'd still, because we have this much extra time here. Right? But chances are this clock period is set by not one particular circuit, it's set by the worst case circuit ever in our whole design. One of the circuits is going to have the most accumulated delay, and that's the one that will determine what the maximum clock frequency can be. We call that the critical path. It's the path that determines the maximum clock frequency. We'll discuss that later. For now, just remember, though, that there's this accumulation. So we can say that T, the period of the clock signal, has to be greater than the time clock to Q plus the time for the mux plus the time for the setup of the flip-flop. Usually written this way, T has to be greater than tau of clock to Q plus tau of mux plus tau of setup. That's the governing constraint. That's kind of the golden timing model rule, the timing rule for CMOS circuits, right, or edge-triggered type circuits. Okay, so now, in general, if you have a system that has lots of different paths, I just showed you one path from one register to another register. As I said before, there's lots of paths. For example, in this, even in the simple one here, we have the path from here to here. We have a path from here back around to there. We have a path from here back around to there and to here. It's always register to register or input to register or register to output. And for correct operation, this equality that I told you about a second ago, that has to be satisfied for all paths, right? If it's not satisfied for some particular path, the signal won't get to the flip-flop in time, and the circuit will fail because of that. It'll capture the wrong value, right? And how do we enumerate all paths? This is just what I said. Any circuit input to register output, or any circuit input or register output to any register input or circuit output. Right? It's hard to do this by hand if you're designing complicated circuits because you have lots of paths. This is one thing that tools will do for you. If you've been using the tools in the lab, they've been looking at reports yet? There is a report that'll tell you what it expects the maximum clock frequency for your circuit will be based on what it knows about your circuit, and it does this sort of analysis for you. It just kind of statically looks, or it just looks at all the paths and figures out which one is the longest path, and it will tell you what your minimal clock period could be given your design. Okay. Yeah, so this notion of setup time and clock to queue applies to the registers, but it kind of also applies to the outputs. So setup time for an output is a function of what it connects to. If this output is going to another register, then that register will have its own setup time. If it's going through a combinational logic block, then into a register, that will effectively increase the setup time requirement for this output. Likewise, for inputs, there will be a little delay after the clock edge before that input appears, right? And that will depend on how it's being generated. If it's being generated directly from a register connected here, then it'll be just the clock to queue delay of that register. But if it's coming out of a register, then through a combinational logic block, then it'll be the delay of the combinational logic block plus the clock to queue of the register. That will kind of give the effective delay at the input. Right. So all that, it's hard to analyze the circuit in isolation. You kind of have to know what it's connected to and what it's driving it, what it's driving and what's driving it. Okay. So let's talk more about this gate delay business. So here's another example here. I think you understand the concept. We have this NAND circuit here. Zeros on the top, so that's a 1. If we change, there's a 1 there, we change that from 0 to 1, then this is going to go 1 to 0, and the output's going to go 0 to 1. So Y will change at some point after X. In this case, we're actually looking at 2 gate delays in series. I said already, modern CMOS gate delays are on the order of a few picoseconds. But it kind of depends a lot on the design of the gate and the context, what it's connecting to. And we'll see what it connects to has an influence on what its delay is. Right. Often, to make it simpler to kind of characterize a particular process technology, we'll talk about FO4 delays. FO stands for fan out of 4. It's a process-dependent delay metric. Okay. FO4, fan out of 4, is the delay of an inverter driven by an inverter 4 times smaller than itself and driving an inverter 4 times larger than itself. This is meant to be sort of a characteristic situation that arises in circuits where we fan out signals to many places. It's just a way to kind of, if we can understand what the FO4 delay is for a particular process, it tells us something about the speed of circuits built in that process. Right. So FO4 for, and it's meant to somehow characterize what a typical logic gate in the middle of your circuit would look like, its context. Okay. So for 32 nano process, I'll show you some more values later. It's around 10 picoseconds. For 7 nanometer processes, around 2.5 picoseconds. Here it is for dependent on processes over time, starting in 1999 when we had 180 nanometer processes, all the way down to 2017 when the 7 nanometer processes were introduced. The FO4 delays have gone from about 77 picoseconds all the way down to this 2.47 picoseconds. Right. The other way to think about this, okay, so now gates appear in series with other gates. So we talk about path delay, which I mentioned earlier. It's roughly the sum of the individual delays of the gates. All right, so if we want correct operation, the total delay of this path has to be less than the clock delay minus the setup time and the clock to queue time. So I just rearranged things here. So this is the total logic delay has to be less, has to satisfy this equation. Right? High-speed processors, the critical paths, which is the worst path, the one that determines the clock period, have around 20 FO4 delays. That means, roughly speaking, there's about 20 logic gates in series, worst case. And again, people have kind of looked at, we can look at this over time. This is CPU clock periods expressed as FO4 delays. And remember, over time, so as we move to the right, we're getting more and more modern processes. So FO4 delays are shrinking. But the other what this shows is the number of logic gates in series, or the number of FO4 delays in a single clock period, is also shrinking, right? So what this tells me is, if you think about the pipelining in the processors, the pipeline stages are getting shorter and shorter, right? Fewer stages of logic per pipeline stage over time as we move through time. If you look at this, yeah, so the pinnacle of that, the ultimate of that was the Pentium 4, which had 20 pipeline stages in the processor. If you don't know what processor pipelining means, don't worry about it now. We'll be talking more about this in a few weeks when we talk about the RISC processor. Now, this is kind of the historical limit of about 12. If you follow this further in time, what happened after the Pentium 4 is actually the curve started going the other way. The processors started having fewer and fewer pipeline stages and more stages of logic per pipeline stage. And this is mainly for energy efficiency reasons that we'll talk about in a few weeks. Okay, so what determines the actual delay of a logic gate? I need to watch the time. Well, transistors are not perfect switches. They can't change terminal voltages instantaneously. That's really the short story. So if you consider, let's say, a NAND gate, we had this connection. If I have 1 here and a 1 here, and we change one of those 1s to a 0, we'd expect the output to go from a 0 to a 1. Right? Changing the output from 0 to 1, that means we have to change the voltage at the output. So what's going to happen is this transistor that's associated with that change here, it's going to go from a 1, which means that was off previously, to a 0, which means that one is on. It's now conducting. So it's going to give us an opportunity to connect the output to VDD, change the output from a 0 to a 1. Now, some current will flow here. The amount the current flows depends on the process that we're using, but also the transistor size, as we discussed last time. Wider transistors, literally ones that are laid out to be wider, bigger, will produce more current per unit time, or more charge per unit time, a higher current value. Right? And that will allow us to switch the output quicker, because switching the output, really what that means is changing the voltage on that node. This node has some capacitance associated with it. Right? And capacitance comes from various places, as we'll see. But for now, you can just imagine there's a capacitor here, and that's the value on the capacitor that we're trying to change. That's the process of changing the output from in this case, from a 0 to a 1. It's charging up the capacitor. Right? And really what the capacitor does is effectively integrates the current, or integrates the current. The current is a charge per unit time, and the charge all accumulates on the capacitor, and the voltage on the capacitor changes. Right. So it's going to look kind of like this. Voltage will change, and then as it gets closer and closer to VDD, this transistor will source less and less current, and then pretty soon it'll kind of asymptotically approach VDD. And it's kind of exponential-like, right? If this were a resistor and charging a capacitor, we know that this would charge it like an exponential. And we can kind of approximate it that way. But it turns out that this device isn't really a resistor. It kind of looks like, when there's a high voltage across it, it looks like a current source, meaning the amount of current through it is independent of the voltage across it. So this will be kind of a straight line. And then as it gets less and less voltage across it, it gets more like a resistor. And then it will get more kind of an exponential shape there. A lot of people just treat it as a resistor, and this is pretty close to being an exponential, right? But for now, the important thing is that the time that it takes to change the output is directly proportional to the amount of capacitance there, and inversely proportional to the amount of current. So we can make the gate switch faster, have less delay in getting the output from one value to another, and get it to switch faster by using wider transistors, sort of. It's a double-edged sword, though. If you make this transistor wider, then you increase the capacitance that the gate has. And so the stage before it will get slowed down. So it's not a, we'll get into more of that later, but it's kind of a tricky business. The other thing is to be careful about the logic layout and try to decrease the amount of capacitance here. And we'll talk about where that capacitance comes from. There's some built-in capacitance here in the transistor. There's capacitance in the wire that connects to other logic gates. And then the inputs to other logic gates are gate connections into MOS transistors, and those gate connections have a certain amount of capacitance. All right. So we lump all that capacitance together for now and call it C sub L. Okay, so that's kind of the dynamics of how the gate is changing its output. And I still haven't really told you where, this kind of explains where gate delay comes from, but I'll say more about that in a few minutes. When we cascade gates together, there's a really interesting behavior. Okay, I think I said this. The transistors actually act like a cross between a resistor and a current source. The so-called ISAT, the maximum current that we can get out of a transistor, is when the gate voltage is fully charged and there's a maximum voltage from source to drain. Right? That's this amount of current here. That's proportional to the width and the length of the transistor. As I said the other day, usually we make the length minimal, and then we just design transistors of different strengths by using transistors of different widths. You can think of this as like putting multiple transistors in parallel, and they all work together. So you get to add up the current of all of them. And then in FinFETs, we use multiple fins to get to a wider type transistor. Okay. The physical layout determines the transistor strength. As I said, here you can see these transistors on the bottom are this wide. The ones on the top are wider. Right. Now, okay, I think I said all that. The other way to kind of envision this, in case you're not getting it, and the way I think it's useful to think about it is there's kind of, think of electrons as water molecules and the transistors as pipes, where the width of the transistor is kind of the width of the pipe, the diameter of the pipe, and the capacitors are like buckets, right? So really, when we connect the input of an inverter to 0, we want the output to go to a 1. That's effectively charging the output capacitor, filling this bucket with water, and the pipe is that P-type thing here, right? And then if we change the input to the inverter to VDD, we'd like the output to go to 0, and that's effectively discharging or draining the water out of that bucket. And so the strength of the transistor is kind of the diameter of the pipes, and the size of the capacitor is the size of the bucket. And in CMOS, all we're really doing is moving charge around. We move charge from the power supply to the capacitance of a gate, or from the capacitance output of the gate down to ground. So it's really like static electricity. We're just moving charges around, and that's all it is. So it's very simple to understand. Now, we like to do things mathematically, so the only way you can really do that, because the transistor is a nonlinear device, it's hard to formulate the differential equations, the equations of motion for changing these voltages for nonlinear devices. So to keep things simple, we linearize the model of the transistor, as I said the other day, and we assume that it's a resistor. Right. Sometimes. A lot of people do that. A lot of textbooks do that. If you do that and you look at the low to high transition, or the high, here's the high to low transition, it's kind of just what I was talking about before. The model looks like this. The input to the transistor is the gate, and I said the gate acts like a capacitor, so there's a certain amount of, if you want to affect a circuit, first you have to charge up the gate of that, looking into that circuit, in this case an inverter, so it'd be the sum of the capacitance of the P and the N-type transistor. Once it is doing its action, we can model the P-type as a resistor. It has a certain amount of conductance, and then the output is a capacitor. So this is a resistor and a capacitor. And we know then this is just RC. We know this is a first order ordinary differential equation, the solution of which is an exponential. So in this case, it's going to go from, and so it looks like, the solution looks like this. The voltage as a function of time is some initial voltage times e to the minus t over RC. Right. So as t progresses, is this discharging? It's 1 over t. Oh, this is actually, which way is this going? We go from V, sorry. Yeah, RC is minus 1, e to the minus 1. Yeah, time 0. This is 1, so we start at V naught. Right, so this is exponential decay, right? So we start at some voltage, and as time progresses, we get exponential decay. So that's the pull down. And the RC here is the product of the resistance here and that capacitance. So we can see if we make R bigger, we can get less current per unit time. It takes longer. Right? Or if C gets bigger, it takes longer. Okay, and one more thing here. Because this is exponentially approaching 0. Right? Or the other one exponentially approaches V naught, which is VDD in this case. It doesn't ever actually get there. So we need some way of characterizing the delay here. Okay. So we'll pick this point. If this is VDD, we could pick this point, which is VDD over 2, which is and then measure this time. So this is the time that it takes to get halfway there. And that's here, where turns out this is long base 2 times RC, because I forgot how you get it right now. But yeah, if you plug in, solve for V naught over 2, you get that time. is equal to log base 2 of RC. So, and this is 0.69. So we know that the delay of the circuit to get to halfway will be 0.69 times RC. And we'll do more of that next time and look at it for some other logic gates as well. And I think that's, oh yeah, so that's here. So we call that the delay high to low. In this case is 0.69 times R times C. Okay, I think I'm going to end there. Next time we're going to talk about what happens when you cascade gates together. And the short story is the delays basically just add up. Right? You take the delay of that plus the delay of that plus the delay of that, and that'll give you the delay through the whole cascade. And that's a nice property also about CMOS. And that's because the dependence of the input on the output is pretty nonlinear. So once you get about halfway, nothing happens. Before halfway, once you get past halfway, the output is changed. So they act kind of independently of one another, and you can just kind of add together all their delays. Okay, good. So I'll see you next Tuesday.